Hello everyone. In this video, we're going to talk about the topic of heteroskedasticity in linear regression. Well, in the beginning, because it has a very crazy name, it might uh, sound not easy to pronounce, and it might seem like a hard topic, but if we see beyond that and then just pay attention to what it really means, it's going to be a simple concept to cover. So eschedasticity is the second part of this name is related to the variance of error term. So heteroskedasticity means that the variance of the error term is not homogeneous, and it's not constant in a sense, and it differs based on different parts of your data set. And as opposed to a homoskedastic situation, when you have homoskedasticity, when you have constant variance and you have homogeneous pattern when you look at your data, and when it comes to variance of your data. So in linear regression, one of our main assumptions is that the model should be homoskedastic. If you remember, when we define the equation for our linear regression and we define that error term at the end, and we said that the error term should be normally distributed with mean of 0 and a constant variance of sigma 2. We might not know what that value is, but we have that very important assumption that we know it's constant. It's the same thing for every error in our model or in our data. So if in other terms we say that the error terms should be normally distributed, or IID, they should be independently and identically distributed from a normal distribution. So if this sigma 2 is constant, they're going to be identical, but if they come from different sigma 2's, then they have different values for their variance, then we are violating that assumption. We can see it here. For instance, if the error terms are each coming from a normal distribution with mean of 0, so it's still surrounding 0, but the variance is a different thing based on the observation that you're looking into. If you visually want to look at a case of homoskedastic when we have the constant variance, this is our data y, and then we can look at it in a scatter plot versus x, and we can see that this pattern of x increasing and then y is increasing with x as well. We kind of can see that like we have this scattered points on our plot, but they're kind of bounded in between these two parallel lines that are straight and parallel together. Now, if we take the residuals of the model of like y given x, we can see that it's basically this shape is rotated and coming to be almost symmetric around 0, because these are the error terms. So we can see that the mean is 0, and then the variance is again kind of bounded. We might not have that many observations on our tail of the data, but we can see that they are not very different from the rest of the space. But if we want to look at the non-constant case where we have the heteroskedasticity, we can see this, for instance, this two cases. In the first one, we have the case of increasing variance, As x increases, we can see that the spread of our data is increasing too. Those two straight lines are not going to be parallel anymore. The bottom of x values, they're closer, and the gap is getting wider as x increases. Same thing happens when we look at the residuals. So now, again, the residuals have mean of 0, but the variance of residuals is smaller here compared to the right side of x, the right tail of x. That's where we can see that the residuals at the right tail of x could have higher variance than the one the left, although they all are surrounding 0. And this is the decreasing case, which is very similar to the increasing variance case, just with the opposite direction. So the above examples were kind of showing cases of heteroskedasticity, that the variance was gradually changing as we were moving on our data access. However, sometimes you could have, other situations. It doesn't need to be gradual change. Sometimes you could have um, one part of your data is over here, and then all of a sudden it drops down, and the other part is a little lower, or one part of it is with wider variance, and one part is with a shorter variance. So maybe it comes from two different groups, and one group has like a smaller variance than the other group. Um, Sometimes it could be a function of a variable, that is your the error inherently is related to one of the variables that you're using, or a function of one of those variables. So at the end of the analysis, there is still some correlation between your error term and your variables. Thus, your errors are not going to be IID, and then they're not going to have the constant variance for um, every locations of your data, because they're related to that. So at some points they're going to be higher, and at some points they're going to be lower. So often when you work with variables like income, population, and time, situation like this going to happen. We will see a very similar example to this in one of the cases that we will review the R code for it. So if we want to explain a little more on types of situations and examples that those variables could cause case of heteroskedasticity, we can think about talking about income, population, and time. You can think about, for instance, as we have a lower income level, our purchasing power could be different. So our utility function could be different, and then as we get higher levels of income, we might get access to more options, more variety of products that we can choose from. So then the price, or um, the distribution of price or demand of those goods are going to be different for people who are coming from higher income level than people who are coming from lower income level. For instance, if you're poor, canned tuna is a good source of protein. As you become healthier, you can eat more of it, or you can eat less. You have the options, but you also have options to do other stuff. You can spend a little more on automobiles, clothing, housing, and also you can spend a lot more on those stuff compared to when you didn't have that much wealth. So it would be it would be different variance when you're looking at data distribution of data like this based on the income level. So when you have a situation like this and you neglect it or you don't pay attention to it, you don't diagnose it, so you end up with case of heteroskedasticity, then that's gonna have some consequences and problems for you. The first thing that you need to remember is that the point estimates for all this regression is going to be the same. So what's going to happen is just like if you imagine this line that was going up and then you bring it down, that's going to be the zero line over there. Again, the line that's going to pass through these points and try to be in the center of them, still going to be in that center. So um, nothing going to happen to your coefficient. Situation like this, the line was going up at this angle, similar to the same angle, it's going to go up like this. But what's going to happen is because the variance is the problematic thing when you have case of heteroskedasticity, you have a non-constant variance, then you cannot really trust the results of any test that is dependent on your estimation of a standard error. So you cannot really trust the accuracy of your estimates because standard error is a measure of accuracy or precision. For instance, when you are dealing with t-test and um, you want to figure out whether the null hypothesis could be rejected, the null hypothesis that is beta is equal to 0, you need to calculate the t-statistic, and the t-statistic needs to use the beta hat and the standard error. So beta, how we said, it's going to be the same, it's not going to be different between these two cases, but the standard error in this case going to be different in that case. And if we just neglect those assumptions that we had a non-constant variance and we don't know that we have a case of heteroskedasticity, then our variances for our betas are biased, and they actually that leads to underestimating the coefficient variances because we think the variances should be smaller, but it's actually larger. That means the result of our t statistics and f statistics going to be invalid, so we cannot have valid inferences either from them, and basically the model that we are describing could be completely wrong because standard errors are very important in defining whether you have significance or not. And if we have the wrong significance assumptions, then we're gonna have invalid inference. So in the case of neglecting the heteroskedasticity and then assuming as we have a case of homoskedastic data, then the null hypothesis tend to be rejected too often. We're going to have too many cases of false positives. So what can we do? Well, sometimes just visually looking at these stuff, you can figure out that you have case of heteroskedasticity. That's why we are talking about data visualization being the first step in any data analysis, to just like figure out what you're dealing with, what type of tools and tests you need to deal with the rest of your analysis. So we can visually inspect it. We talk about white test, and then basically a bunch of other tests that are very, very similar to the y-test. So, and Bruce-Pagan test, that's one of those super similar tests to y-test, and that's basically one that we're going to use in practice. It's a subset of y-test, so a specific case of Bruce-Pagan test is the y-test. And we use BP test function in R that is coming from package lm test. So make sure that you install package lm test, otherwise you cannot use this function. And there are these other variety of these linear model tests for lm tests that are going to be used for case of heteroskedasticity. Just they are very similar to each other. They just have different specifications. So the concept is very similar between all these tests. They all want to test whether you have non-constant variance or different variance, but they're coming from different the specification based on the domain of your problem. We talk about that a little bit more. So what is the how does white test work? Um, Mr. White, he he started to develop this methodology that is based on the definition of heteroskedasticity. We know that definition of heteroskedasticity is coming from non-constant variance. Variance is estimated based on, or standard error is estimated based on the errors or residuals that you have in your problem. So it started looking at the residuals, and it said if the residual is going to show some pattern versus my right-hand side variables, then I know that they I have that case of non-constant variance across my right-hand side variable. So in the first one, nothing happens. In the second one, something happens. So he said, hey, let's go to these residual values. You can see they have positive and negative values. And it said, I can see that it's very narrow here and it's get wider down there. So he started to take the square of these residuals and call them, like residual squared or whatever. Now everything gonna become positive, and if you imagine all these stuff that are at the bottom gonna come to the top, and again, because absolute value of these numbers here are smaller than absolute value of these numbers over there, we're gonna have this increasing pattern of residuals, as opposed to this case that if you get the square of these guys, everything gonna come to bounded again on a straight line. So he said, when I get the straight line, I know that there is no relationship between the square root of residuals and my right hand side. But when I get a pattern like something going uh, up, not a straight and horizontal, parallel to the x-axis, and it goes up like when you imagine the square root of these residuals are larger here and smaller over there, so we're going to go up, then it knows that there's an increasing case of variance by x. So in order to do that in practice, he first needs to run the first model. From the first model, get the residuals, and then get the oldest residuals from the regression model that is the main regression model that we are studying, and we want to see if we have a case of heteroskedasticity. And then estimate an auxiliary regression, which the residual squared are the dependent variables. So the left-hand side of that auxiliary regression is the residual squared, and the right-hand side variable of the original models are in the right-hand side, plus the squares of them, plus the cross products of them. So after that, he gets a new R squared from the auxiliary regression, and that's the number of observation, and multiply that. He proves that this is going to be a chi-squared um, random variable with m degrees of freedom, and that's going to be the test statistic, and goes to that distribution to see what kind of p-value it gets. If it gets low p-value, then that means that okay, there is the relationship between the residual squared and right hand sides are not zero. There is at least something on the right hand side that is affecting the residual squared. So you have case of heteroskedasticity. But if it gets high p-value, then you don't have the case of heteroskedasticity. The Bruce-Pagan test, as we said, is basically um, um, could be a custom version of white test, because you can have a specific right hand side variables. You don't have to just use these guys, but any Bruce-Pagan test, if you just use these specification of right hand side variables, it turns into a white test. So Glaser test, instead of using the residual squared, it used the absolute value of the residuals. Harvey-Godfrey used the log squared of the residuals as dependent variable. So the idea for Harvey-Godfrey test is that the relationship is not between the residual squared and the right-hand side values in the linear form, but it's uh, in a in an exponent form. So that's why they take the log of the squared residuals. Park test is similar to Harvey-Godfrey. They also get the take the log of the right-hand side variable, so it's a double log specification. Goldfield's quant test is being used when you can see natural separation of your data into group or groups. So into groups. So you can you can annotate your groups in the data. For instance, if they're coming from 2 different years, or they're coming from 2 different locations, similar, maybe like neighboring states or neighboring counties or something like that, and or 2 different age groups. And then what you do, you separate your data between those 2 groups and run your linear model, calculate the residual sum of squares for both your models. You have different number of observations, perhaps in your models N1, N2. You have same model in both cases, so you have same number of parameters, and then you get these 2 residual sum of squares divided by the degrees of freedom, the ratio of those two from those 2 models, give you an F statistic, and similar that you've seen in your ANOVA test. Now, if this F statistic is statistically significant, you have found the evidence of heteroskedasticity. That means that the ratio between these two was, um, F distribution is a positive distribution, so it was further enough from zero that you said, oh, it's significantly away from zero. So, and you say you have found case of heteroskedasticity because they're different from each other. That means one group has a different reduced sum of squares than the other one, smaller or larger anyways. And but if they're similar and they produce similar variance, then these residual sum of squares ratios to their degrees of freedom are going to be similar too. Thus, the F uh, the test value not going to be too far away from uh, 0, 1. And your p-value would be high, and then you fail to reject the null hypothesis, and you have a case of homoscedasticity. Assumptions are okay, nothing is failed, and no assumptions for your linear regression is a model is violated, and you can trust your inference. So what solutions we can use if we have case of heteroskedasticity. I have listed three of them here. First one, we use the wide HCSM estimator. HCSM is the abbreviation for um, heteroskedasticity consistent covariance matrix. So we talk about this more shortly. But I actually like the second and third solution better than the first one, especially the second one. Because in the second one, what you do is you just scale your variable or find an appropriate way with that scaling to make the problem go away. Sometimes, variable transformation like taking a log, taking care of the problem. That's actually most of the times that's the case. Uh, a lot of the times that's the case. And one other way is using weighted least squares or generalized least squares, so rather than just using um, um, optimization models, algorithms in your linear regression that is trying to give you the um, least amount of error for all the um, observations kind of equally with no different weights. In this case, you're assigning weights. So maybe for those observations that have higher amount of error or showing higher amount of variance, you're adding lower weights to it's like a contra effect for that high variance and vice versa. So the HCCMS estimator is when you have your covariance matrix from linear regression with the assumptions that you have homoscedasticity, your covariance matrix is just this first part with basically sigma squared before that, or your estimate before that. But here, if you have case of heteroskedasticity, they use this um, covariance matrix omega that they put it in center of this thing, so you kind of have like this symmetric design around it. And that's why they kind of call it like sandwich too, and the library in R that you use to get these estimates is called sandwich as well. So what it does is creates this covariance matrix for your beta, and then using the new estimates of that matrix, you can um, create the new t-test and new f-test, because your standard errors are now uh, different from the case of homoscedasticity. And based on those new robust standard errors that are coming from this HCCM matrix, then you can make your inference based on that. So, but again, I'm saying that this is way better because you don't have to do any of these you know tricky things that you don't change your estimate at all. You're just changing the standard errors by doing these stuff. So using white ACCM estimator to some extent could be like whitewashing, especially if you have low number of observations. Usually, that these frequentist solutions are working well when you have asymptotic situations. So they could give you good answers when uh, your ends you deal with asymptotic cases, and that means you have a relatively large number of observations, but you cannot expect good performance from them when you have a smaller sample size. So with that, let's go and see this in practice. There is this file, the dataset ATL schools, and then we have ATL schools example, R codes, Atlanta school data. So let's read the data set, and it's a CSV data. Get the structure of our table. We have 6 variables, and there are 44 observations. We have school name and these variables: PPC, DA, MTS, ATT, and PTI. So we have the definition of them here. PPC is per pupil cost, PTR, pupil to teacher ratio. So if I have for every 10 students, if I have 1 teacher, then that would be 10. MTS, monthly teacher salary, DA, average daily attendance, and ATT, person's attendance. Let's could use attached, but no, I'm gonna use lowercase names for them. So let's run those lines, create our variable names. Because I want to use some Bush-Pagan tests later with custom specifications that are going to use quadratic form of our right-hand side variables. I'm creating these squared version of my right-hand side variables as well. Now my first model would be looking at, I want to, there's a focus of this analysis. The analysis is we want to figure out, can we describe what would be the per pupil cost? So if we know what the data about what's the average daily attendance, that is a number that could give us how many people are going into that school on average per day, and a monthly teacher salary for um, teachers in that school, and then what's the percent attendance of uh, students. So if I have these pieces of information, can I figure out or can I describe what would be the per pupil cost for that school? Now, this is my first attempt. Per pupil cost modeled by those 4 fields. So we run that, and then let's look at the summary of it. Gonna go to options, maybe. If it's 20, no, 18 is max, okay. So DA significant and MT is significant. Attendance percentage wasn't that much significant, and then I have PTR, which is pupil to teacher ratio. Now, also, no, I'll mention that F is statistic is coming very significant as well. Now, I need to load this library, LM test, that we talked about, that it's going to have the Bruce-Pagan test that we're going to use. So after loading library, I want to see, am I good with this results that I got? So can I easily use this standard errors and estimates to finish my analysis? Well, I want to check if I have case of heteroskedasticity. So I first do a Bruce-Pagan test. So in this test, your residual sum of squares from model 1 going to be modeled by the right-hand side variables, and then if there is some relationship, you're going to have low p-value. So you reject the null hypothesis that there's no relationship, and otherwise you get a high p-value. So we're running it, and then the result is 6% for your p-value. So it's significant at 10% level, but not at the 5% significance level. Now, maybe someone, a frequentist who uses 5% significance level is done right here. It says, okay, I don't have any case of heteroskedasticity, and this is homoskedastic. Everything is okay, and then we move forward. But no, we're not gonna do that. Let's look at our data. So what we did over there is we got the residuals of our model and then look at the residuals versus our right-hand side variable. And we can see that the residuals are not spread the same as we move along our right-hand side data. And that's kind of the case for all of them, but for the case of DA, it's way more. The variance or the spread is way closer across lower or higher values of other right-hand side variables. But when it comes to DA, I have higher variance in the lower amount of it, and very, very smaller variance in the higher amount of DA. So let's remove DA and see what happens. So this is just visually we looked at it, and now we have our second model that has per pupil cost, MTS, attendance rate, and PTR. So let's run that, and then now run the BP test again, Bruce-Pagan. P-value 79%. So we failed to reject the null hypothesis that there is some relationship between the residual sum of squares and the residual squared and the right hand side, residual squared from the model M1 and the right hand side. And so we know that we have case of homoskedasticity. So we removed DA, problem got solved. However, we're not done because we remove some information. We cannot just say this is our model. We throw one of the fields out because it was causing some problems, and now we're done with it. Well, to really see exactly explain a little more about what's going on when we're doing Bruce-Pagan test or white test, you remember these steps. In practice, we have to first obtain the oldest residuals from the first model under consideration. So here, my main model under consideration is M1 because it had DA first, and it was. I want to see if I had a case of heteroskedasticity. Here, I'm taking the residuals of it, so that's obtain all those residuals, and then after that, take the square root of it. Estimate it. Auxiliary regression with the residual squared. So I get the residual squared, I call it ResSQ. Now I have this. So in these steps, I'm just explaining what's going on with basically white test or Bruce-Pagan test. And it says use as a left hand side, and for right hand side, use the specification of Bruce-Pagan that is just like original right hand side in the model. And we do that and get the summary of M3, and you can see that in that we get DA, a significant variable with residual squares. So it shows relationship between residual squares and DA. So there would be different residuals, different variance based on different values of DA, non-constant variance, thus case of heteroskedasticity. We cannot trust our inference because all of this is based on the assumption of homoskedasticity. So now that we established that, so this was just showing in practice what's going on in the background of a test like this BP test M1. That's actually what's happening in the background. The p-value of it you don't see here because that p-value is based on this, and it's going to be chi-squared distribution. There is no report of chi-squared test statistic here, but you can see that DA was the one that was showing significance. Now, this is an example of doing custom BP test. That is, if you want to have different specification for the right-hand side of your Bruce-Pagan test, not just the original uh, right-hand side value. So in this case, I'm using DA2. I can add these other ones as well, so I can line them up. So let's run this first. We can see it shows 1% when I added that one. So it's kind of compared to when I didn't have that, it was just 6%. But when I added the DA squared, I can see that that even got better. So if the frequentist statistician was using this custom one, even at the 5% significance level, he couldn't fail fail to reject the homoskedasticity, and he has to reject the homoskedasticity and know that, oh, I have a heteroskedastic model. Now, this is what they do in a lot of people, and especially, again, this is a way that frequentists deal with it, but Bayesians coming with calculating the covariance matrix too. So it's not just limit them, but these functions are functions that are generally using HCCM estimates based on traditional methods. So we load library sandwich. Here we want to calculate this covariance matrix, and then based on that covariance matrix, go and calculate these new values, because the standard error is going to be different, and then we want to see I'm sorry, we want to see these new values. That's our original model, and then see how the standard errors change and how the significance level is going to change. So because I'm going to load that, I'm going to first run the summary of M1, the original one, the one that is based on homoskedastic assumptions, and then using HCCM matrix. This is the specification that we use. We call model 1, and then coef test would give us the coefficients t-test results. So it will give us something similar to this part. So let's run it. So we ran summary M1 and we got this. We ran coef test and then we got this block. And we can see that here everything got less significant because standard errors were underestimated here. After we made the correction, the standard errors are larger. And making standard error larger, then you get less accurate, so your significance gonna change. Your p-values gonna get larger, so you're not as significant as before. Now, what's gonna have to our f-test results, the Wald test function, using that specification, gonna give us the f-test that we can compare with this line. So this time we can see that overall our model is still significant. So our f-test is significant too, but if you compare the p-values, this is in order of minus 10, 10 to the power of minus 10, this 10 to the power of minus 6. So still very significant, but less significant. Now, as we pointed out in this part, I'm not gonna this is not really my favorite way of handling this, so we should this is also lazy way, so it's easy, it's quick and easy to do it and get away with it, get done with it. But if you make some more effort to um, make some other changes, scale your variables or weight your results, then you know weight your residuals when you're estimating your model, then you know that could be better because you're using the data in a more informative way rather than just you know you're not you when you use the HCCM matrix, you're not doing anything to the coefficients estimates. Let's look at these estimates again. The only thing that is changing between these two is the standard error. So standard error is changing, but the estimates are exactly the same. So if you can make some transformation and get a sensible model that use all your data, then you will have also new estimates too. So those estimates could be more trustworthy. And another thing is just drop the variable that was causing the problem and don't deal with that one. So we're not going to do that here. Let's go with the second solution. So we want to scale this problem. What we're going to do, we go with per pupil cost. Instead of modeling per pupil cost, we're going to model total cost for um, students. That would be if we multiply daily attendance by pay pupil cost, then we get that total cost. Again, if anyone wants to convert it back, it's as easy as dividing it by the DA, the daily attendance that they were using. So now we didn't throw the DA out as opposed to the case here, and we are keeping it, and we have it in our right hand side, and we use this in our left hand side. By the way, I kick ATT out because ATT was not significant in any of our models. So now we can run that, and let's run the Bruch pagan test for M5. Now the p-value is 0.83, very, very high p-value, so we can be sure that the data is homoscedastic. We run our model. Now we see that, okay, as teacher salary is going up, that we can see it has a positive effect on the total cost for the students. The more expensive the teachers, the cost for students in that school going to be higher too. The daily attendance, you have total cost is definitely a function of total number of students. If there are more number of students going to that school, it's going to be higher cost in that school too. And pupil to teacher ratio has a negative effect. So if the number of if you have a lot of students but just one teacher for them, so if the ratio is high, that should have negative effect on the cost because you're kind of saving cost by just assigning one teacher for a lot of students, but no, you're not going to have a good quality of education. You're kind of compensating for that. It's a trade-off. And the third one is using the weighted least squares. So what we're going to do is we want to use dA and we use W as inverse of dA. So for the high values, they're going to be multiplied by a very, very smaller numbers because the higher value the dA, it's going to be higher um, uh, if lower variance. So 1 over dA gonna have a smaller number, and if dA is a small, 1 over dA gonna be a larger number compared to when dA is large. So in this case, because dA gonna be used in the weight, we cannot use it in the model itself. And We use per pupil cost, teacher salary, and pupil to teacher ratio. Here we use the weights option in the LM function in R, and then we call W there as we defined it before, and this is going to be my model 6. We run that, and we can see that as um, teacher salary go up, average per pupil cost goes up. As pupil to teacher ratio goes up, the average per pupil cost goes up. And you can see that these are kind of all ratios or averages on both hand sides, and it's a sensible model to look into it like that. I'm sorry, I think I said goes up, but that goes down just like the negative effect it has before. These estimates are different from each other in size because in the left hand side here you have the total, but here you have per pupil, not per student, not total, so it's going to be smaller. This is it. Thanks for watching.